Good afternoon, everyone. Welcome to Compass Seminar on Wednesday afternoon. Today's speaker is Yu Gao. Yu is a graduate student from the Department of Mineralogy and Physical Oceanography. She graduated from Ocean University of China in 2016 with a bachelor's degree in marine science and joined RSMAS in the same year, 2016. Her research interest is in mesoscale ocean dynamics and airsea interaction. Welcome to the Compass Seminar, Yu, and the stage is yours.
Thank you everyone for coming to my seminar. The title for my seminar is Mesoscale airsea coupling and mixed layer variability in the Southern Ocean. So here is the structure of my seminar today. First of all, I will be talking about motivation and background. Second, I will be talking about the model description. Third, the mixed layer heat budget and the mesoscale airsea thermal coupling. Fourth, the mixed layer depth variability and the relevant processes. Fifth, the response of mixed layer depth variability to mesoscale airsea coupling. And the last section would be the conclusions. So first of all, the motivation and the background behind the study. The motivation behind my study is that unlike large-scale airsea interaction, the mesoscale airsea interaction is ocean-driven. The observational analysis and numerical studies shows that the ocean drives the mesoscale variability in airsea heat exchanges. By that, we mean the correlation between SST anomalies and turbulent heat fluxes are positive. When the ocean is warm, it releases heat to the atmosphere. And when the ocean is cold, it absorbs heat from the atmosphere. That's what we call an ocean-driven airsea interaction. And resolving such mesoscale coupling at the airsea interface can help improve the climate predictability. However, the current generation of the climate models, such mesoscale coupling are not very well resolved. On the top, I showed a SST field of the Southern Indian Ocean in the CCSM4 simulations. At this plot, you can see the tip of the Africa and part of the Agulhas current and part of the subantarctic frontal region. And as you can see in the top panel, when the ocean resolution is 1 degree, where the Agulhas current is very vague and very weak, and the frontal region also is very weak. However, when you increase the resolution to 0.1 degree, the ocean is actually full of eddies. And this is actually much closer to what we actually observe with satellite and all kinds of observational analysis. And also the strength of the Agulhas current is increased and the strength of the front is also increased. And since we are interested in the SST variabilities and SST anomalies, what we propose to do is to analyze that by diagnosing the upper ocean heat budget. There have been studies by Tamsid et al. Looking at the mean heat budget in the upper 614 meters in the Southern Ocean. And it is between, they found it is between the airsea heat flux, which is top panel, panel A, and the total heat advection, which is panel B. That is a term created by the ocean currents. And the temperature tendency, which is the last panel, is a smaller term. And the second to last term is a diffusion, is an even smaller term. And all the panels in between are the decomposition of the oceanic advection. And we aspire to do a similar type of analysis, but with our own model, and consider a variable mixed layer instead of a fixed depth, which is 640 meters in their study. And we will look at a balance at a mesoscale lens instead of at a large scale lens. So the reason we want to consider the mixed layer depth, the variable mixed layer depth, is because the mixed layer depth in the Southern Ocean exhibits very strong seasonal and mesoscale variability. Here I show an example by Dong et al. 2008. They analyzed the Argo float profiles and objectively mapped the monthly average MLD. And here they used the definition of a potential density threshold definition, which is also what we will use in the study from now on. And in here, we can see that in January, for example, in the whole domain, the mixed layer is mostly under 50. Some regions at the frontal region is between 50 and 100 meters. But when you go to June, July, August, the average value increased to hundreds of meters of mixed layer depth. And then as the austral summer approaches in the November, December month, the mixed layer start to get shallow again. And the reason we want to consider that is because the mixed layer depth can modulate the ocean heat budget and air-sea coupling by changing the effective heat capacity of the upper ocean. For the same amount of heat, if the mixed layer is thin, the surface temperature would increase a lot, relatively speaking. But if the mixed layer is thick, then the same amount of heat won't create as much of a temperature increase in the surface. So next, I will describe the model we use. So we will use the regional ocean atmosphere model by Perling et al. 2020. The ROAM is a fully coupled model with an idealized ocean component and realistic atmospheric forcing. It uses a nested system with an outer atmospheric domain of 27 kilometers horizontally, and horizontal resolution, and an inner atmospheric domain that's 9 kilometer resolution horizontally. And we mainly analyze the ocean component, which is 2.5 kilometer resolution horizontally, and has a 30 sigma layer vertically. And the ocean domain is 2,800 kilometer long and 1,120 kilometer wide. The maximum depth is 3,000 meters. And it is, as you can see on the right-hand side, it is formulated in two separate regions with two different oceanic regimes. So we have two sets of different simulations. One is called the weak current case. It has a weaker current. and has smaller meridional temperature, as you can see from the top panel here. And at the bottom, you can see it is the SST from the strong current case. It has a larger meridional temperature gradient in the ocean model. So here I will show the annual mean current speed and the direction in the stream plot, and the water depth in the strong current on the top. It's reversed in this slide. Actually, from now on, it's reversed on the strong current on the top and weak current at the bottom. So as you can see, there are contours in the middle. It shows there are 12 randomized seamounts placed to the floor in order to keep the net zonal transport close to a reasonable value. And the annual mean current speed in the strong current case is clearly higher than the weak current case, hence the name. And we can also tell there is a meander, also a jet, in the strong current case between 800 kilometer and 1,000 kilometer in the y direction. So using that model, we will analyze the mixed layer heat budget and the mesoscale air-sea thermal coupling. And in this section, we will emphasize three things. First of all, the important role of oceanic heat advection. And second, how MLD, mixed layer depth, modulate the heat budget. And third, the scale dependence of the budget and coupling. On the right-hand side, it is a diagram showing the processes that we are mostly interested in. It includes airsea heat flux, the heat advection within the mixed layer, the diffusion and entrainment, the shortwave heat flux at mixed layer base, and the variable mixed layer depth. And here is a equation we use to compute the ocean mixed layer heat budget. And all terms here are integrated over a time-dependent mixed layer. On the left-hand side, we have the tendency term, which is also called a mixed layer heating cooling term. On the right-hand side, the first term is the heat advection term, which is the contribution by the ocean currents. And the second term on the right-hand side is the diffusion term, which is computed by the residual in this case. And the third term is the surface heat flux. Sometimes we call it the diabatic heating term. So in order to look at the scale dependence of this budget and the role of oceanic advection, we also look at different filters. For example, we look at mesoscale and zonal anomalies separately. Here, the mesoscale SST anomalies are defined as a departure from a 300 kilometer by 300 kilometer running average. And zonal SST anomalies are defined as a departure from the zonal average. In panel B, we can see the mesoscale SST anomalies. And in panel C, we show the zonal SST anomalies, and also the stream plot associated with that. As you can see, the zonal SST anomalies mainly include the stationary meanders and are mainly large-scale features that are visible in panel A, the full SST. While the mesoscale has a smaller spatial scale and also a smaller magnitude. Since we consider MLD variability to be a very important modulator, we also computed the domain average and standard deviation of the MLD. And in both SC and strong current and weak current case, the MLD reaches its maximum in September and its minimum in February. So they both show very similar seasonalities. And this seasonality is very consistent with previous studies by Dong et al., by Sali et al. So it is safe to say that our study recreates the MLD variability of the Southern Ocean. And the domain average MLD varies from tens of meters in summer to hundreds of meters in winter. So the drastic changes in MLD can modulate the heat budget, which I will show you in the next slide. So in the zonal mean, monthly mean heat budget, here in the strong current case, we can see that when the mixed layer is shallow in austral summer, February, panel A, the diabatic heating term in blue is a dominant term, and the other three terms are relatively small compared to that. And starting in June, the advection term becomes the advection term in the red line becomes more comparable to the diabatic cooling term. And from September to November, when the mixed layer is rather deep, reaches the maximum, the advection term start to dominate the mixed layer heat budget, and it explains almost it explains most of the mixed layer heating and cooling. That is the red line representing the total advection almost overlaps with the black line, which represents the mixed layer heating and cooling. And when you go to the December, when we enter into the austral summer, the mixed layer is shallow again. Then the diabatic heating term takes the dominance in the heat budget again. In the weak current case, however, there's a difference, mainly because the current or the strength of the advection is weaker. So here, the diabatic heating term, the blue line, seems to always dominate the budget, although its dominance decreases as the mixed layer deepens. So from June to September, when the mixed layer is deep, the advection term is in phase with the mixed layer heating and cooling term. So for example, if you look at panel C, the meridional variability in the mixed layer heating and cooling is very consistent with the total heat advection, while although the diabatic heating term is a big term, the variability is created by the total advection. So that is what happens in the total budget or the zonal mean budget. And what happens in the high pass filter budget or the mesoscale budget? So that's what we are very interested in. So we took the whole budget and high pass filter that with a 300 kilometer and by 300 kilometer filter. And here is what we find. On the right-hand side, we show a term by term decomposition of the budget in a high-pass filtered budget. So in A and B, we show the heating and cooling in February and September, respectively. Notice the color bars are different. One is 50 maximum and one is 500 maximum. And C and D are the heat advection. And here it's very obvious that the mixed layer integrated advection term accounts for the majority of the mixed layer heating and cooling in both February and September in the strong current case. And in panel E and F, the mesoscale airsea heat fluxes, or the diabatic heating term, is a smaller term. And they are not correlated with the heating and cooling. And the last two panels, the residual terms, are also very small, which represent the diffusion term. So similar story here in the weak current case, in terms of high pass filtered budget. The heat advection is the most important term in the budget. However, the advection here is weaker compared to the strong current case because of the weaker current speed. So in order to more easily look at the relative importance of advection to diabatic heating, so to compare oceanic variability to atmospheric thermal forcing, we did a simple scaling analysis in the heat budget term. So it is the advection term, mixed layer integrated advection term to the diabatic heating term in this number. And this number depends on two variables mainly in this scaling analysis, which are the mixed layer depth on the x-axis and the current speed, which is represented by the advective time scale on the y-axis. And the red dots are the strong current case, and black dots are the weak current case, and these are computed by the monthly mean values in our simulations. So we can observe a rather interesting seasonality here. For example, in February and December, I would say Austral summer, the ratio is very close to 1, between 1 and 2, which means that at this time, the advection and diabatic heating as a whole at the basin is probably equally important because of the thinner mixed layer. While when you move to June, the advection is, since the ratio of that advection to diabatic heating, then the advection, the number is around 8 in the weak current case. That means the advection is 8 times more important than the diabatic heating term, and in the weak current case. And that is 20 times more important than diabatic heating terms in the strong current case. And in September, that's even more dramatic numbers. So in order to look further into this question of large scale versus mesoscale, we also did a more complicated nonlinear decomposition, which is computed as follows. So we would subtract a large scale advection computed by the mean velocity and mean temperature and integrate it over a variable mixed layer depth, and subtract that from the total advection, and then count that as the mesoscale advection. We would do this separately into mesoscale, which is a 300 by 300 kilometer running average, or a zonal anomaly, and in order to see the scale dependence of this study. So what we are most interested in are two variables. First of all, the mixed layer heating and cooling term. So how does the mesoscale advection contributing to the mixed layer heating and cooling? So in the zonal anomalies, the mixed layer heating and cooling has a pretty positive and linear relationship with the zonal heat advection anomalies, while it has a, as you can see from panel B in the red line. Now we are only talking about the strong current case, and the relationship is rather nonlinear and not as strong in the weak current case. However, in the mesoscale decomposition, this relationship is rather weak, which means that the mixed layer heating and cooling is not directly caused by the mesoscale advection under the 300 kilometer filter. And the relationship is also more linear in the strong current case compared to the weak current case. So next, since the other variable that we are interested in are the SST anomalies itself, because SST anomalies is a very important variable in the airsea coupling. So in panel A of this plot, we show the mesoscale heat advection in the shading, and the SST anomalies in the contours. So the blue means the mesoscale heating, and oftentimes co-located with warm SST anomalies. And the mesoscale cooling in the blue oftentimes co-locate with cool SST anomalies in panel A in the strong current case. And this is a monthly average. We also find the same pattern throughout the year, and we also did other analysis to make sure this pattern is robust. So now, but this relationship is not as strong, or this correlation is not as strong in the weak current case, which you can observe in the panel B. And in panel C, we show that the turbulent heat flux in the shading, which is if it's red, means it is the ocean absorbs heat. So the ocean would absorb heat when the SST is colder, and the ocean would release heat when the SST is warmer. So that means the ocean drives the airsea heat flux. So the message I want to convey in this plot or in this figure is that the mesoscale heat advection would create the SST anomalies, and these SST anomalies would in turn create the turbulent heat fluxes. at the mesoscale. However, we did not observe the zonal SST anomalies having this relationship with the zonal heat advection anomalies. So let me summarize part 3. So the focus of this part is on the role of mesoscale currents in the mixed layer heat budget and airsea coupling in the Southern Ocean, and the relationship between mesoscale advection and SST variability is determined by ocean current strength and MLD. At mesoscale, the mixed layer heat advection is the main process that sustains SST anomalies in the regions with strong currents. This relationship is, in contrast, significantly weaker in the weak current case. And the SST anomalies are damped by the airsea turbulent heat fluxes. And the effects of atmospheric forcing, such as thermal and wind forcing on the upper ocean, are modulated by the MLD variability. Since we found the MLD variability to be important, the next part would be looking at the mixed layer depth variability and the relevant processes that contribute to that. So here is a study by Li and Li. It shows the annual revolution of the MLD in the vertical cross sections in the subantarctic frontal region. This is it shows the core of the frontal region in the shading, and the line are the mixed layer depth. So the deepest mixed layer depth occurs around September, and it has a tendency to be located at the equatorward flank of the subantarctic frontal core. In order to examine which processes contributes to the mixed layer depth variability, we will look at the buoyancy budget in the Rome simulation. We will analyze the same simulation as the part 3, but this time, instead of the heat, we'll analyze the buoyancy. So we will do a 3-part budget. The first part is the tendency, which is the buoyancy frequency tendency, which I'll call the n-squared tendency. When it's positive, means the water column has a stratifying tendency, and the mixed layer depth will get shallower. And when it's negative, the water column would have a destratifying tendency, and the mixed layer depth will get deeper. On the right-hand side, the first term is the term we'll diagnose with the simulation. It is the buoyancy advection shear, and the residual term, and which we will call the atmospheric forcing and mixing term. This is a term that is hard to quantify directly, thus we will count it as the residual. So first of all, let's look at the evolution of the mixed layer depth in the Rome simulation from month to month, and look at whether the n-squared tendency line up with that. So in this figure on the right-hand side, the shading shows the n-squared tendency. In red means it has a stratifying tendency. In blue, it means it has a destratifying tendency, and the mixed layer would get steeper. So from January to March, that's the summer in the Southern Hemisphere, the mixed layer as section this is a section plot at x 1,000 kilometers. So it is rather shallow from January to March, although in March, we can start to see some of the destratifying signals around the mixed layer. Starting in April, that's when we really see the strong destratifying tendency around the mixed layer. The mixed layer is the red line, the white line in the middle. So this destratifying tendency prevails from April to July. And the mixed layer deepens very consistently with such tendency. And in August and September, the mixed layer depth reaches its maximum at this section. And in the September, it has a wedge-like shape. In October, it has a very strong shoaling signal, which is a stratifying tendency around 50 to 100 meters depth. And in November and December, it has a rather mixed signals in November and a strong stratifying signal in December. And it continues to get shallower and shallower in the summer season. So I would say the n-squared tendency we diagnose is very consistent with the mixed layer depth variability we diagnosed. So the next question would be, which process contributes to the n-squared, the stratifying and destratifying tendency? Is it the oceanic advection or the atmospheric forcing? So this is the dichotomy we try to look at. So first of all, we look at the oceanic advection shear. In January to March, there's really not much to look at because of the shallow mixed layer. Starting in April, that's when you really have the strong stratifying signal instead of the destratifying signal shown in this tendency in the n-squared tendency term. So I would say the advection shear has the reverse effect of the tendency. Instead of contributing to the tendency, it's actually counteracting the tendency of the mixed layer. And what's really contributing to the tendency of the mixed layer is the atmospheric forcing and mixing. And that doesn't really mean the atmosphere, that doesn't really mean the oceanic advection isn't important, because if you take out the oceanic advection shear term, the budget would be wrong because it's a big term in this analysis. So the now going back to the atmospheric forcing and mixing term, from April to July, you can tell that the major destratifying signal comes from the atmospheric forcing and mixing, and it is very consistent with the n-squared tendency we diagnosed. So now we have looked at what it looks like in the vertical section. We are ready to integrate it over the mixed layer depth. The reason we want to look at it that way is because we want to look at the mixed layer advection shear in under a different lens. So if the buoyancy advection at the surface in the equation below is larger than that at the mixed layer depth, then the advection term has a stratifying tendency, and the mixed layer would get shallower. And if the buoyancy advection at the surface is smaller than that at the mixed layer depth, then the advection would have a destratifying tendency and the mixed layer will deepen. So the reason we want to do this analysis is to produce maps. So we want to look at whether this pattern we observed in the section plot is consistent in the two-dimensional field. So it turns out it is, but it also has a seasonality. Let me explain. So first of all, let's look at the January 2016. In Austral summer, when the mixed layer is relatively shallow, the mixed layer integrated budget shows that the atmospheric forcing and mixing, which is the residual in the B panel, is pretty consistent with the n-squared tendency in the A panel. And the advection shear in the C panel is a smaller term. However, it contributes to a lot of the mesoscale structure of the jet region of the tendency, and both at the tendency term and the residual term. And in the beginning of austral winter, when the mixed layer starts to deepen, both at this stage, all three terms are important because previously only the tendency and atmospheric forcing are important. And this at this time, both advection and residual contributes to the tendency term. So the sum of advection and residual contributes to the n-squared tendency. Although at this time, since it's winter, the mixed layer deepens, it has a negative tendency. So the atmospheric forcing mixing still plays a bigger role, still have a positive correlation with the tendency, and the advection shear has a negative correlation with the tendency. And in September, however, when the mixed layer reaches its maximum, at this time, both advection and residual still contributes to the tendency term. However, at this time, the tendency term become a much smaller term than the residual and the advection term. The dynamics is still the residual contributes to the tendency, and the advection counteracts the atmospheric forcing and mixing. So let me summarize part 4. The mixed layer depth variability, we conclude, is induced by the atmospheric forcing and mixing, while the advection shear counteracts the atmospheric effect. In the mixed layer integrated budget, the dominant terms changes as mixed layer depth varies seasonally. In summer, atmospheric forcing and mixing causes the majority of the tendency, while the advection shear is a smaller term. In winter, atmospheric forcing and mixing are negatively correlated with advection shear, while tendency is a smaller term. So on top of the mixed layer depth variability, the causation of the mixed layer depth variability, we also want to look at the response of mixed layer depth variability to mesoscale airsea coupling. So we designed 2 sets of experiments to facilitate that purpose. First of all, the Smooth-Fluxes experiment. In the Smooth-Fluxes experiment, the ocean is forced with large scale of sea surface heat flux instead of the large scale plus mesoscale surface heat flux. And in this setting, the atmospheric thermal damping effect is significantly weakened. So originally, if there is in the control experiment, if the turbulent heat flux damps the SST anomaly, then there will be a negative correlation between SST anomaly and turbulent heat flux. However, this correlation is weakened in the Smooth-Fluxes experiment. The purpose of that is to look at how the atmospheric feedback on SST anomalies affect MLD variability. And for the Smooth-Winds experiment, we would look at the ocean component forced with large-scale wind stress instead of the full wind stress. And the SST wind stress coupling is significantly weakened in this experiment compared to the control experiment. So in the control experiment, over warm SST anomalies, the wind stress would increase, and over cold anomalies, the wind stress would decrease. And this correlation is decreased or weakened in the smooth wind experiment. And the purpose of this experiment is to see how the mesoscale wind stress affect the MLD variability. And first of all, we would look at the potential density and the MLD. We chose one section at a y direction, in the y direction. This is 10-day average field. We observe a very consistent large-scale potential density structure, and the MLD differences between the three cases are mainly due to the local potential density differences. And across the three experiments, we observed that the SST anomaly or the SST variabilities in the Smooth-Fluxes and Smooth-Winds case is increased because of the lack of the atmospheric damping, especially in the Smooth-Fluxes case. And because look at the B panel in the domain average root mean square of SST anomaly differences. This is the control minus Smooth-Fluxes case in the red and control minus Smooth-Winds in the blue. And for the red line, the difference is rather large in the January to the May, to May, which is summer to the beginning of fall. So that's when the mixed layer is rather shallow. And when the mixed layer is deeper in winter, that's when the thermal inertia is rather larger in the upper ocean, and the SST anomalies are not very sensitive to this type of differences, which you can observe in from May 2016 to September 2016. So how about the MLD anomalies, which we are most interested in? So the mesoscale MLD in anomalies in Smooth-Fluxes and Smooth-Winds case also have significant differences from the control experiment. The domain average anomalies in the control case exhibit higher magnitude compared to the smooth fluxes and smooth winds case. And this differences is bigger in winter when the mixed air depth is deeper. The reason we assume the mixed layer variability is suppressed in the control experiments is because of the presence of the mesoscale airsea coupling. So in this, since we already look at the domain average statistics, we would also be interested in the two-dimensional differences between the experiments. For example, this is the annual mean mixed layer depth between control and smooth fluxes case in the panel B, and between control and smooth winds case in panel C. So as you can see, there are lots of dipolar structures in the jet region, which means we have positives and negatives. In some regions, there are positives. In some regions, there are negatives. And we hypothesize that it's probably related to the shift and the speed change of the jet, since we already observed the same structure of the dipolar shift in the stream plot and current speed in the control minus, for example, the control minus smooth fluxes case in panel B. We have this dipolar shift, the green next to the red at the jet region, or next to, I would say, slightly south to our jet region. And the stream plot also shows that the difference is mainly mesoscale and it has an eddy-like structure. So next, in order to look at this problem more deeply, we decided to look at the two sections, which is 1,000 kilometers around here and 2,000 kilometers around here. So for time's sake, let me just look at 1,000 meters because they are pretty similar. For example, here, the current here in the 1,000 kilometer in the smooth fluxes case. If you compare the current between 800 and 1,000, you can see the smooth fluxes case, the current gets stronger. This is the monthly mean in August 2016. It gets stronger and also slightly shifted, but not very obvious. But in 800 kilometers, the flow shifted very obviously southward. And it also has a more bigger span than the control case. And we take the mixed layer depth difference and the depth average speed difference. And we look at the correlation coefficient between the two, and we find out that they are pretty well correlated. So where the speed difference dips, the mixed layer depth difference also dips. So we would say the mechanism could be that the mesoscale airsea coupling or the lack of airsea thermal damping actually modified the current in the smooth fluxes case. which lead to the change in the mixed layer depth. But still, this is a very new question, and it's a work in progress, and I welcome questions and suggestions from the audience. So very similar ideas from other sections and the smooth winds case. With that, I would summarize my part 5. In the smooth flux experiment, the ocean component is forced by large-scale heat fluxes, and the airsea thermal coupling is weakened. In the smooth winds experiment, the ocean component is forced by large-scale wind stress, and the SST wind stress coupling is weakened. And mesoscale airsea coupling damps the mesoscale MLD variability in the Southern Ocean, according to 2 sensitivity experiments results. The response of annual mean MLD to mesoscale airsea coupling varies spatially, most likely due to the shift of jet position and change in current speed in the sensitivity experiments. And lastly, I will state the overall conclusions from my study. First of all, the mixed layer heat budget of the Southern Ocean, we conclude that the oceanic heat advection creates SST anomalies, while atmospheric turbulent heat fluxes dampen these anomalies. And this study links heat advection, SST anomaly, and airsea heat fluxes at mesoscale, and emphasizes the overall dominance of intrinsic oceanic variability in mesoscale airsea heat exchange in the Southern Ocean. In the heat budget, the effects of atmospheric forcing, including the thermal and wind forcing on the ocean, are modulated by the mixed layer depth variability. And the buoyancy budget analysis shows that the atmospheric forcing and mixing induces the variability in mixed layer depth, while the oceanic advection counteracts these effects of the atmospheric forcing. The oceanic advection of heat and buoyancy are important processes that should be considered in the climate models. The mesoscale airsea coupling damps the mesoscale MLD variability in the Southern Ocean, according to the 2 sensitivity experiments. The response of annual mean MLD to mesoscale airsea coupling varies spatially, most likely due to the shift of the jet position and changing current speed due to the mesoscale airsea coupling changes. With that, I conclude my seminar. Thank you.
Okay, thank you very much for the nice and long presentation. We got a lot of presentation for the money today. Payson sent me a message that it's too noisy in his office now because they are doing an experiment in the wave tank. So I will do the questions and answers. So if someone has a question, please switch on your camera and unmute your phone, your microphone, and ask your question. More questions? Comments? Well, if there are.
I have a question for you.
Yes, please.
Right. Giselle, in the beginning, you mentioned that these mesoscale airsea interactions are important for climate variability. Can you clarify a little bit on what you mean?
Climate predictability?
Predictability, yeah, I'm sorry.
Yes. So there are studies coming out that showing with higher resolution simulations, we would get much closer to what we actually observe in the reality instead of lower resolution. So I think that's a pretty solid testament to why we should increase the resolution of the climate models.
Thank you.
Yes.
Okay, then Lisa. Lisa was first, right?
Oh, Yu Yang, you go first.
Oh, it's me? Okay, thank you. I have a question. Why
Yes.
do you choose to examine both the heat and the buoyancy budget?
Because do you mean in terms of the its contribution to mixed air depth?
Yes. Do they tell the same story of the relation between mesoscale and the mixed layer depth?
No,
Okay.
because in the Southern Ocean, the saline saline profiles and the temperature profiles compensate each other, and actually the potential density is a better representation of the mixed layer depth, and in this so naturally a better budget to analyze in terms of the mixed air depth variability is a buoyancy instead of the heat.
Okay.
Yeah.
Okay, thank you.
Hi, Giselle. That was a really nice talk, very well put together. Thank you.
Thank you.
I have a question that's kind of, I guess, quite broad in a way, but I was wondering if you could comment on whether your results, whether you feel that your results are in keeping with the paradigm of the Southern Ocean eddy compensation mechanism. And in that case, whether you can make kind of any inference about, you know, what your expectations might be, for example, for, you know, future meridional heat flux in the Southern Ocean.
Yeah, actually, part of the study that's not shown here, we decompose the eddies and the mean. We found out that the eddies compensate for the mean in terms of the heat budget. I don't know if that's what the type of answer you're looking for. But yeah, in terms of the meridional eddy heat transport, we actually considered that in the sensitivity experiments. It's just that we haven't got around to it. We want to look at whether the meridional heat transport is significantly different in all the three experiments: the control experiment, the Smooth-Fluxes experiment, and the Smooth-Winds experiment.
Yeah, I guess I was wondering if you might be prepared to, you know, infer based on the very detailed understanding that you now have of the system, what you think, what your expectations for the results of such an experiment would be, right?
Yeah, you mean hypothesis, right?
Yeah.
Yeah, I don't know. To be honest, I don't know. I have to be honest.
Okay, I think that was all. Then thank you again for this nice long seminar. Thank you all for watching it. We recorded it for YouTube, so you can watch it again later this evening. And as an announcement, I can say We will have David Riglitsky of the National Hurricane Center on Friday morning in the next seminar. I don't know how to pronounce his name, but that's how I pronounce it. And next Wednesday, we have Henry Potter, a former AMP student who is now a professor at Texas A&M. And next Friday, we will have the first 3 15-minute student seminars. So I hope to see many people there. And that's all for today. I wish you a nice evening. Thank you for coming.